Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will explore the Olivia Linux cluster using the Cray module system. Specifically, we will use the math kernel library, MKL, to perform matrix multiplication, leveraging OpenMP for parallel computing. In videos 42, 43, and 44, we use the Cray Fortran compiler loaded through the Cray module system. In videos 45 and 46, we switch to the Intel Fortran compiler loaded through the NRIS module system. In video 47, we use the Intel Fortran compiler again, but this time it was loaded through the Cray module system. In this video, we will also load the Intel Fortran compiler through the Cray module system. We will also do a scaling analysis. This analysis involves measuring computation times while varying the number of threads, starting with a single thread and scaling up to 256 threads. Scaling analysis is a technique in parallel computing used to assess how effectively a system performs as more processing units are added. It helps identify whether increasing computational resources leads to performance improvements and to what extent. This process is vital for optimizing parallel systems and ensuring resources are utilized efficiently. I am already logged into Olivia and currently inside the MXM, OpenMP, Cray, Intel folder. I will list the contents of this folder. We will begin by examining the Fortran program that performs matrix multiplication using MKL. I will open the program with the Emacs editor. I will use a matrix dimension of 32, 7, 68, and this Fortran program was previously reviewed in video 43. I am using allocatable matrices in this program. The reason for using allocatable matrices was explained in video 43. I will now exit the Emacs editor and return to the terminal. Let us take a look at the job script used to execute the MKL Fortran program. The script is largely similar to the job script discussed in video 43, but in this case, I am using the Cray Intel programming environment. As in video 43, I will utilize the math kernel library, MKL, which requires loading the Cray scientific libraries that include MKL. The script compiles the Fortran program using the Cray Intel Fortran compiler with only the FOpenMP and O3 options. Unlike the NRIS Intel compiler, which required the X-host option, the Cray Intel compiler automatically applies CPU-specific optimization through loading of the AMD Turin module, which was done above. Additionally, The compiler options needed to use MKL with the NRIS Intel compiler are unnecessary with the Cray Intel compiler, as this is handled by loading the Cray scientific libraries, which was done above. After exiting the job script, I will return to the terminal and clear it. I will execute the Fortran program by submitting the job script to the Slurm queue system. We can see that the job is assigned the number 4295. Using the slurm queue command confirms that the job has already finished. I will use the more command to open the slurm job output file. The job output file first lists the modules that are used by the job. The matrix multiplication using Cray Intel MKL was completed in about 7.2 seconds with 256 cores. We can see that the job used about 44 gigabytes of memory. This is the same memory usage as in videos 43 and 44. This increased memory usage is a trade-off for better performance. The computation time using the Cray compiler loaded through the Cray module system was approximately 5 seconds, as observed in videos 43 and 44. The computation time using the NRIS Intel compiler loaded through the NRIS module system was about 8.5 seconds, as observed in video 46. Here, we see that the computation time using the Cray Intel compiler is approximately 7.2 seconds. This indicates that the Cray Intel compiler is not able to achieve the same level of optimization as the Cray Fortran compiler when using the MKL routine. As a result, the MKL routine with the Cray Fortran compiler is approximately 1.4 times faster than the MKL routine with the Cray Intel compiler. I will now perform a scaling test, but let me clear the terminal first. To begin, I will list the contents of my folder. I will use the Python script, named Setup Testing OpenMP, to conduct the scaling test. The script uses the OS module to execute Linux commands and was previously reviewed in video 44. The scaling test also uses the script named Testing OpenMP, as in our previous videos. This script will not compile the Fortran program, but use the executable I just generated in this video using the MXM OpenMP MKL job script. We can take a look on this testing script. The script is very similar to the Testing OpenMP script we used in video 44. The only difference is that it uses the Cray Intel programming environment. After exiting the Emacs editor, I will clear the terminal. I have the Python module in my home environment, as explained in video 44, and will begin the scaling analysis by executing the Python script. The terminal displays the sbatch commands executed by the script. Applying the show queue command confirms that all my jobs have started. Before checking the results, I will clear the terminal. First, I list the content of my folder with the ls command. I use the more command to look at the last slurm output file. From this file, we can see that the module load commands in the job script has switched to the Cray Intel programming environment. We can also see that using 256 threads with MKL results in a wall time of approximately 7 seconds. The job output file shows that the CPU efficiency was about 89% and the memory usage was about 44.5 gigabytes. I used the data from these scaling tests to create figures showing the wall time and CPU time. The figure displays the wall time and CPU time with a logarithmic scale on both axes. Let me first enter the number of threads or cores used in the scaling analysis. I can add the mean wall times to the figure. I will enter the CPU time calculated by multiplying the wall times by the number of cores used. Finally, I include the speed-up factors between tests. The reason for plotting the CPU time is that this curve would form a straight line if the scaling analysis had shown a perfect speed-up factor of 2 for all tests. We observe a near-perfect speed-up up to 16 cores. The scaling analysis shows that a computation taking about 612 seconds on a single core is reduced to approximately 43.7 seconds on 16 cores, achieving a speedup of around 14. In an ideal scenario with perfect speedup, this would have been 16. The speedup decreases when scaling from 16 to 64 cores. The scaling analysis indicates that a computation taking approximately 43.7 seconds on 16 cores is reduced to about 14.8 seconds on 64 cores, achieving a speedup of roughly 3. In an ideal case with perfect speedup, this would have been 4. The speedup decreases further when scaling to 256 cores. The scaling analysis shows that a computation taking 14.8 seconds on 64 cores is reduced to approximately 7.20 seconds on 256 cores, achieving a speedup of 2.1. In an ideal case with perfect speedup, this would have been 4. The scaling analysis reveals that a computation requiring 612 seconds on a single core is reduced to 7.20 seconds on 256 cores, resulting in a speedup of about 85, which remains below the ideal speedup of 256. A perfect speedup is unattainable because, as explained in video 11, there will always be sections of a program that cannot execute in parallel. These sequential sections increasingly limit the speedup factor as the number of cores used for parallel computing grows. As observed in these scaling analyses, there is near-perfect speedup up to 16 cores, but this diminishes when scaling to 32 and 64 cores. The speedup factor declines even further when utilizing 128 and 256 cores. In the next video, we will summarize the scaling analysis performed on Olivia and compare it with the scaling analysis conducted on Fram and Betsy. I am looking forward to the next video. Wishing you all happy computing in the meantime.